classical theory of electron theory, classical, okay, theory of free electron. Okay, and then is quantum theory of free electrons. So classical theory is basically also called Dürrday theory, Dürrday-Lorentz theory or Dürrday theory. Okay, and your quantum theory of free electrons. Okay, that is called Sommerfeld theory. These are scientist names, okay, which have given these theories. So classical theory, okay, it has some shortcomings, okay, but still it gives some basic ideas of metal properties. Okay, so using this classical theory as well as this quantum theory, we are going to explain basically metals. Okay, so because in metal we have sea of electron. Okay, we say the charge carriers are in metals are electrons. Okay, so in 1900 J.J. Thomson invented electron. Okay, discovered electron, and just 3 years later, okay, Dürrday gave a classical theory. Okay, he told that the charge carriers in the metals are electron. Okay, and he combined this existence of charge carriers with classical gas model. Okay, and he is able to explain some properties of metal. Okay, so what are those properties we are going to discuss? Okay, so number one is the DC electrical conductivity. Okay, DC electrical conductivity. Okay, I hope you are getting what I'm saying. Okay, so we are trying to see some metal properties. Okay, we are going to explain metal properties.
Sir, your video is
Sir, there is some
Okay,
problem.
some of metal properties like, yeah,
hello.
yes, yes.
Sir, the video is getting blur and your voice is also not coming properly.
Okay,
Sir,
just
थोड़ा सा network issue हो रहा है.
yeah, I understood that today we have not connected this internet wire. Okay, I am in some other room. Can you connect internet wire because they have getting some lag? Okay, just give me 1 minute.
सर आपकी आवाज भी नहीं आ रही है.
आवाज तो आ रहा है ना अभी? Okay, I think should not be blurred.
Sir, it is blur.
There may be shadow, but
Still blurred, sir.
blurred.
सर नेटवर्क प्रॉब्लम है सर.
नेटवर्क जस्ट मुझे कनेक्ट नो वायर कनेक्ट करने दो. ओके, Extra. Any improvement? Can you see now improvement?
No, sir.
No, still I connected with LAN wire also.
Sir, actually today audio and video are not working properly.
Oh no. Okay, audio is not also coming.
No, sir. When you sir, it's taking time to deliver to us.
Audio is there say lagging. Is the problem in this mic? आवाज से आ रही है?
आवाज तो ठीक आ रही है मैम पर
Okay. So
अब
ठीक है ना? Okay. So can I continue now? Okay. So we are going to explain some of the metal properties like DC electrical conductivity, okay, and Hall effect, okay. Then we'll also discuss Weidmann French law, okay, and some optical properties of metal, okay, optical properties. Of metal, okay. So I assume that you know these things, okay, like what is Hall effect, okay, Weidmann French law. Anyone? What is Weidmann French law? Any idea? Okay, so this is basically, this law tells about the ratio of electrical conductivity versus thermal conductivity and optical properties, okay. Now these things we are going to discuss first using Duraday theories, okay. We are going to discuss this first, Duraday theory, and we'll see Duraday will be able to explain, okay, some basic concepts about these properties, okay, but there are some shortcomings, okay, and those shortcomings, when we'll treat this one from quantum free electron theory, and there those concepts will be clear, okay. So let me start with the Duraday theory. Okay, so put the heading Duraday theory, okay, or this is also called classical free electron theory, okay, classical free electron theory, okay. So there are some assumptions of these theories, okay, we have to understand before we discuss this thing, okay. What are the assumptions of this theory? So number one is electron behave like a classical gas molecule, okay, okay. So electron in solid behave like a gas. So the electron, okay, electrons in solid, okay, behave like gas molecules, okay, and these electrons, okay, do not interact with each other, okay. So there is no Coulombic interaction between these electrons, okay. So the electron behave like a, because this was the classical theory in 1900, in the beginning of 1900, okay. So people mainly know classical theory, okay. So Duraday is trying to combine, okay, electron with a classical gas theory, and he's trying to explain the metal properties. So the electron in solid behave like a gas, okay, and the electron, okay, electrons do not interact with each other, do not interact, okay, with each other at all, with each other at all, okay. This assumption is also called, independent free electron theory, okay. Independent free electron approximation, okay. So according to this approximation, okay, electron do not interact with each other. Now the number 2 point is the positive charge carriers, okay. In metal you have positive charge carriers, okay, you have metal, okay. How do represent a metal? So in metals we have ions, okay, which are fixed. We have ions, and there are sea of electrons, okay. these electrons are free to roam inside. Okay, so these are electrons, and here they are fixed ions. So positive ions are fixed. Okay, positives are fixed or located. Okay, and form immobile. Okay, they are not mobile. Immobile. Okay, immobile cores. Okay, and electrons. Okay, electrons collide with these ions and get scattered. Okay, so these are some important points which are mentioning. So electrons do not interact with each other, but they get scattered with the ions. Okay, and during the scattering, okay, once they scatter, their velocity also changes. Okay, so the electrons instantaneously velocity. Okay, instantaneously instantaneous. Okay, instantaneous velocity changes. Okay, due to scattering. Okay, and this is called your free electron approximation. Somebody mic is on, please. Okay, so I have talked two approximation. One is independent free electron approximation. So independent free electron approximation is always valid. Okay, it says electron do not interact with each other, and in reality they do not interact with each other. Okay, and another one is your that electrons collide with the ions, and because of this collision, their velocity gets altered. Okay, so this is not always true, especially when we are at low temperature. Okay, at low temperature electron do not scatter with your lattice. Okay, so this is a two important assumptions. Okay, there are some couple of more assumptions which are also important. Okay, so because I am treating electron like a free electron gas. Okay,
Sir, in the second point, what you have written this one word I'm not getting. Sir,
so
after immobile
cores.
Oh.
Immobile cores. Okay, and the third point is that the electron reach thermal equilibrium. The electron, all these assumptions are important. Okay, we are going to use all this. Okay, the electron reaches thermal equilibrium. Okay, thermal equilibrium through collisions with lattice. Okay, collisions through lattice. Okay, so this basically, this is what this assumption means. Okay, that the kinetic energy, okay, the kinetic energy of electron, okay, that is half m bt square is equal to 3/2 kT. Okay, so because they are following classical gas, so their energy is 3/2 kT. Okay, at room temperature. Okay, at room temperature, that is 300 Kelvin. Okay, your bt, okay, the velocity of electron, thermal velocity of electron is almost equal to 10⁵ meter per second. Okay, that value is important, you need to remember. Okay, and the last point, which is also very important. Okay, so because electron is colliding Okay, so the probability, yes, okay, the probability of scattering, the probability of scattering, okay, with lattice is equal to probability of scattering is equal to 1 by tau. Okay, and tau is your relaxation time. Tau is your relaxation time. Okay, and your relaxation time is related with your mean pre-path. Okay, so mean pre-path will be what? Vt, thermal velocity, okay, into time. This will be your mean pre-path. Okay, and at room temperature, okay, at room temperature, your tau value is almost minus 10 to the power minus 14 second. Okay, okay, now let me explain these assumptions what I'm saying now. Okay, so this assumptions, first assumption that electron do not interact with each other. Okay, second approximation क्या है? Second approximation है कि electron get scattered with lattice. Okay, and when they scattered, their velocity get changes. Okay, and the third approximation is the kinetic energy is given by this equation. Okay, half mv square, because there's a law of equipartition of energy. So electron energy we can write as a 3/2 kBT. Okay, and the probability of scattering is 1 by tau. Tau is a relaxation time. Okay, and mean pre-path. So mean pre-path is what? Mean pre-path means the distance, okay, electron travels between two collisions. Okay, so when electron in the lattice, okay, it is continuously colliding. So we have a metal, okay,
Sir, can you repeat the mean free path?
yeah, mean pre-path means is the distance covered by electron between two collision is called your mean pre-path. Okay, and relaxation time is what? Okay, the time between two collisions. Okay, when electron is not getting scattered. Okay, so what is happening when electron is in the crystal? Now because of thermal energy, it's is moving and it's colliding. Okay, it's colliding with your scatters and it's not moving anywhere. Okay, so at thermal equilibrium, when there is no electric field, equilibrium, okay, the average velocity, average thermal velocity of electron is 0. Okay.
Sir, thermal equilibrium means?
Thermal equilibrium means, now suppose I have crystal, okay, and I have kept it at certain temperature. Okay, now a certain temperature, I am not applying any other thing, any other force. Okay, so still electrons are, because of thermal energy, still electrons are moving. Okay, but their motion is random. Okay, so we can assume that electron average velocity is 0. Okay, isn't it? If electron has an average velocity, then you should have a current. Yes or no? Okay, so if your sample is kept at some temperature, so if you measure current, you get a 0 current. That means what? The electrons are not moving. Okay, electrons are still moving, but they are not moving in certain direction. And since they are not moving in certain direction, you don't have any electric current. Okay, so now what happens when we apply electric field? Okay, so when we apply electric field,
सर रियलिटी में इलेक्ट्रॉन दो इलेक्ट्रॉन के बीच में कोई इंटरेक्शन नहीं होता है?
रियलिटी में नहीं होता है
सर क्यों सर? इलेक्ट्रोमैग्नेटिक फोर्स क्यों नहीं अप्लाई होता है?
भी इलेक्ट्रॉन तो लैटिस ज्यादा इलेक्ट्रॉन में कैसे, इलेक्ट्रॉन में इंटरेक्शन का मतलब क्या है? भी इलेक्ट्रॉन तो वही बहुत 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 स्मॉल पार्टिकल है, बहुत ही वो है, ठीक है, तो उसमें इंटरेक्शन का कोई मीनिंग ही नहीं है। जैसे गैस मॉलिक्यूल में इंटरेक्शन होता है ना आपका, गैस मॉलिक्यूल तो फिर बड़े होते हैं, वो दे कैन कोलाइड। इलेक्ट्रॉन्स आर सो टाइनी पार्टिकल्स। ओके, सो उसमें इंटरेक्शन का कोई मतलब नहीं है, इंटरेक्शन कोई इम्पैक्ट नहीं है, ना तो इलेक्ट्रॉन का इंटरेक्शन से उनका कोई वेलोसिटी चेंज होगा, कुछ चेंज नहीं होता है। दैट्स व्हाई वी से they do not interact with each other, okay, because they
सर
are
मेटल में तो सी ऑफ इलेक्ट्रॉन है, तो
हाँ
उसको
तो
तो एक रिजल्टेंट इलेक्ट्रिक फील्ड और मैग्नेटिक फील्ड होना चाहिए।
कहाँ होता है, होता कहाँ है, होता है क्या बिना बिना किसी
हाँ मतलब क्यों नहीं होता है सर?
इलेक्ट्रिक फील्ड कैसा होगा, क्योंकि अगर आप मेटल को करोगे बाहर तो कोई इलेक्ट्रिक फील्ड आएगा नहीं ना, टोटल चार्ज तो जीरो हो जाएगा ना, टोटल चार्ज तो जो एज तो मेटल था, एज द न्यूट्रल है ना, न्यूट्रल है मेटल तो पूरा, ओके। And their velocity, I'm also telling, the thermal velocities are, they are not moving in particular direction, so they are not giving any current effects, okay. Average velocity is zero, so if you get magnetic effect only when you have certain electron moving in certain direction, there is no current, okay, no magnetic effects, okay. So हाँ
अगर सर इलेक्ट्रॉन मतलब पहली बात तो इस आपस में कोलिजन नहीं कर सकते, ये जैसे ही कोलाई मतलब करेंगे कोलिजन तो वो रिपल्शन भी तो होगा सर, कुलम रिपल्शन भी।
वो भी हम मान रहे हैं कि उनके अंदर रिपल्शन भी नहीं है, okay. Classical model assuming there is no electrons are not interacting with each other at all, okay. So far आपने जितना भी थ्योरी पढ़ा होगा फिजिक्स का, कहीं पे भी आपने कोई इलेक्ट्रॉन का इंटरेक्शन पढ़ा है?
नहीं सर, लेकिन कूपर पेयर्स और सुपर कंडक्टिविटी में
वो भी थ्रू लैटिस के थ्रू है ना?
हाँ जी सर, यस सर।
तो
सर यहाँ पे सर यहाँ पे जो ये मतलब जो आयंस है उनके साथ इलेक्ट्रॉन का इंटरेक्शन ही होगी।
हाँ उनके साथ तो हो रहा है ना। सेकंड नंबर पॉइंट इज दैट द इलेक्ट्रॉन गेट स्कैटर्ड विद आयंस, ओके, यही तो सेकंड पॉइंट है। इलेक्ट्रॉन में इंटरेक्शन नहीं है, बट इलेक्ट्रॉन विल interact with this ions, get scattered with ions, okay.
तो उनकी वजह से तो वहाँ पे फील्ड हो सकती है।
फील्ड कैसे होगी, क्या फील्ड होगी, जैसे फील्ड क्या होगी, ओके जब तक आप बाहर से फील्ड नहीं लगाओगे, ओके उसका रिवर्स फील्ड तो होगा नहीं, टोटल चार्ज तो जीरो ही है ना। आप किस फील्ड की बात कर रहे हो? इफ यू आर मेटल यू कैन अज्यूम मेटल लाइक ए चार्ज, ओके, यू कैन नॉट अज्यूम मेटल एज ए करंट कैरिंग कंडक्टर, ओके। सो जो करंट नहीं है तो मैग्नेटिक फील्ड नहीं होगा, और वैसे चार्ज जीरो है तो इलेक्ट्रिक फील्ड नहीं होगा, बाहर तो कोई इफेक्ट तो करेगा नहीं उसके अंदर, ठीक है। अंदर तो अट्रैक्शन रहता ही है, चार्ज कैरियर्स और इलेक्ट्रॉन के बीच में अट्रैक्शन रहता ही है, ओके। चार्ज कैरियर्स और इलेक्ट्रॉन में अट्रैक्शन रहता ही है, तभी तो इंटरेक्ट हो रहा है, ओके। बट इलेक्ट्रॉन के अंदर कोई रिपल्शन, कोई किसी तरह का कोई रिपल्शन नहीं है। आर यू गेटिंग माय पॉइंट व्हाट आई एम सेइंग? ओके, सो नाउ so what happens when you have a metal piece, okay, this is at, okay, thermal equilibrium, okay, with no electric field, okay, with no applied field, okay. Now if you apply field, okay, with field, okay, so with field what will happen? Still there will be scatterings. Now you have this metal, okay. Now what will happen if you're applying some field, okay, you're applying some voltage, okay, because of voltage there will be some electric field, okay, electric field will apply force, and because of force this ion will move. Still they will interact, still they will get scattered, but at least they will move in certain direction, okay. So they have some average velocity, they cannot move straight lines, okay, but wo at least move karenge. When you apply electric field, okay, the electron will reach from here to here, they travel some distance, effective distance in time t, okay. There will be collision, and collision will hamper their velocity. You're applying field is trying to accelerate, but because there is a positive ion cores, they will collide, their velocity will go down, okay. So we can say we are applying a field, but there we have some other force also, okay, which is against this motion, okay. That is like a friction force, okay. That force is what is trying to stop this electron, okay. So you are applying field, electron moving, and again their velocity goes to zero. Between two collisions it get accelerate, and again when it collides its velocity gets zero. Again it's require energy, and it takes energy, and the velocity increase. and again it becomes when collides, because electrons are in a mass, the charge carriers are very heavy, ions are very heavy, so as soon as tiny electron collide with this, the velocity becomes 0. Okay, so again, so this process keep happening. So the final result is that the electron, we can consider that electron is moving at a average velocity called drift velocity. Okay, and when you apply electric field, okay, electron move, I'm writing here, when in the field electrons move, okay, with a average velocity, okay, which is called drift velocity. Okay, so this is called your drift velocity, VD. Okay, now let us discuss how this theory can able to explain as metal properties. Okay, so metal properties का मतलब ये क्या है? I told you Ohm's law. Okay, so metals follow Ohm's law. Okay, metals obey Ohm's law. Okay, Ohm's law means J equal to sigma E or V equal to IR. They are both the form of Ohm's law. So metals follow Ohm's law. इसका मतलब है when you apply electric field, okay, the current is proportional, current density is proportional, or current density is proportional to electric field. Okay, and in general we know the electric conductivity is independent of electric field. Okay, so electric field is constant, electric conductivity is constant, and the current density depends on electric field. Okay, that is your Ohm's law. Okay, and the number 0.2 we know about metals. Okay, that about at low temperature, okay, the resistivity of metal is proportional to T5. Okay, and at high temperature, that means above Debye temperature, okay, your resistivity is proportional to T. So if I plot the graph between resistivity versus temperature plot, okay, this is resistivity and this temperature plot. So this graph comes out like this. Okay, so rho is proportional to T above Debye temperature, and in temperature general it follows T5 law. Okay, so these are the two properties about DC electric conductivity.
सर
Okay,
ऐसा होता क्यों एक्चुअली?
कैसा कैसा
कि ये जो लो टेम्परेचर पे T to the power 5 के प्रोपोर्शनल होता है, हाई टेम्परेचर पे सिर्फ T के प्रोपोर्शनल.
तो ये तो एक्सपेरिमेंटली ऑब्जर्व्ड फैक्ट है ना. ओके, when we take experimental results,
कुछ रीजन तो होता होगा, कोई फिजिकल इंटरप्रिटेशन होता होगा.
वही तो हम एक्सप्लेन करने की कोशिश कर रहे हैं. ओके, पहले तो फर्स्ट थिंग तो है कि रेजिस्टिविटी टेम्परेचर पे डिपेंड क्यों करती है. ओके, T power 5 and T is that different thing. Okay? First of all, why resistivity depends on temperature. So you know, when we increase the temperature, what happens? Your amplitude of atom lattice ions, they vibrate with temperature, and as you increase the temperature, what will happen? The amplitude of vibration will increase. Okay, and when amplitude of vibration will increase, what will happen? Scattering will increase. Okay, so when scattering will increase, obviously your resistivity will increase. Resistivity क्या है? Scattering ही तो है. So scattering increase हो जाएगा तो resistivity बढ़ जाएगा. So that is temperature. That's why resistivity depends on temperature. Now why it followed in T laws or T cube or T5 laws? Okay, we'll see now with theories. Okay.
तो सर आपने तो कहा कि अगर टेम्परेचर बढ़ाएंगे तो रेजिस्टिविटी बढ़ जाएगी.
हाँ, बढ़ तो रहा है. रेजिस्टिविटी पर्टिकुलर टेम्परेचर पे कांस्टेंट होता है, पर टेम्परेचर चेंज करोगे तो रेजिस्टिविटी चेंज होगा. सो आई एम सेइंग when you see the metal, okay, मेटल के लिए रो वर्सेस टी ग्राफ क्या होता है? स्ट्रेट लाइन नहीं होता है. Okay, so in general this is only roughly. Okay, if you take any conductor, and you plot T versus rho graph. Okay, so at low temperature is increases, so it's increasing, na? Is increasing as a T power 5. Okay, and when you go above Debye temperature, this increase is dependence is linear. I hope you're getting my point, what I'm saying. Okay, shall we continue? Any doubt? Still any doubt? Okay, so this is our resistivity plot versus temperature, and metal also obeys Ohm's law. Those things we are going to discuss with my Drude theory, and the assumption already we have seen. Okay, let us discuss now these things one by one. हाँ, बोलिए. Yes, you're not audible. Any question?
No, sir.
Okay, so let me write the equation of motion. Okay, for electron. Okay, so when I'm applying force, when I'm applying electric field inside the metal, okay, my electron will get accelerated. Okay, so say the force is EE. Okay, and there are some other forces, okay, scattering centers, which is trying to hamper its velocity, which is trying to decrease its velocity. So as velocity increases, okay, and the forces are proportional to velocity. Okay, so can I write like this equation of motion for electron? Okay, I have a lattice, I'm applying electric field, I'm applying voltage. This voltage will generate electric field, and due to electric field, this electron here, they will experience force. Okay, and because of this force, they will try to accelerate, but they are not getting continuously accelerated, because there are scattering centers. They're colliding with the centers, and their velocity going down. Okay, and so this is the equation of motion. And at particular thing, okay, so when I apply electric field, whether I will get constant current, or I will get keep on continuously increasing current. Okay, tell me. Suppose if I have a sample and I'm applying voltage, okay, so because of voltage I will get a DC current, continuous constant current, or continuously increasing current. बताओ भाई.
कांस्टेंट करंट.
कांस्टेंट करंट मिलेगा ना, तो इसका मतलब एक्सीलरेशन तो नहीं हो रहा है ना. My current is what? My current density is what? NEVD. It depends on velocity. If I'm applying force, electric field is applying force, and because of this force, if there is an acceleration, then my velocity should keep on increasing, and velocity should keep on increasing. That means my current should keep on increasing, and then one point the current should become infinite. But this doesn't happen in the real crystals. You apply electric field, you get constant current. Constant current means what? Your electrons are moving with a constant velocity. That's why I told you that is called the drift velocity. Okay, in the presence of electron, your electron move with a fixed velocity. That fixed velocity is called drift velocity. So in a steady state, what happens? In a steady state, this force is trying to get acceleration, is electric field, but there is a opposing force which balancing this one. When these two will balance, then electron will start moving constant velocity. Okay, then in that case, that is called steady state, and in steady state this dv by dt becomes 0. Okay, so in steady state,
what is this opposing force? What you have written? XV
gamma v.
Okay.
Velocity. Okay, okay, so in steady state, what will happen? Your dv dt becomes 0. Okay, and your velocity become what? Final velocity. The final velocity which with electron move. Okay, that is called your drift velocity. Okay, now let me put this values here. So m dv upon dt. Okay, this is E, this becomes 0. Okay, E minus gamma Vd. Okay, and from here I can take gamma value as, okay, E upon Vd. Okay, so this is my constant. This gamma is constant, and this value is coming out electric field upon velocity. Okay, now I can put this, say this equation is 1. Now I can put this gamma value again here, so I can get m dv upon dt. Okay, E minus E velocity v upon drift velocity. Okay, and this I can write m dv upon dt. Okay, you can put m's and m also here. So my dv upon dt will be what? E upon m. Okay, I'll take constant this one. So this will give me v upon vd. Okay, and I can solve this equation. I can form a differential equation, v upon vd. Okay, and this become e t upon m. Okay, now this is the differential. This is the, you can integrate these equations. Okay, and tell me what will come.
The right side will be dt, na?
Which one? Yes,
So
dt.
E-
Yes, dt. Yes, dt. Now integrate this equation. So if you integrate this equation, what you'll get? So if I integrate this equation, what will come if I integrate this equation?
ln 1 upon 1 minus vd upon
log
minus
of 1 minus Vd.
Minus vd ln 1 minus v upon vd. Correct?
yes
And if we this one, this will be e upon m t plus c. Okay. Now at t is equal to 0, what is velocity? Initial t0 means when we starting applying electric field. Before that, what is the velocity? अरे जब इलेक्ट्रिक फील्ड लगाया नहीं है तब वेलोसिटी कितनी है?
0
0 है, तभी तो करंट नहीं है. Initially velocity is 0 because electrons are moving random motion. There is no net velocity. Okay, so t at t is equal to 0, your v is 0. Okay, so if I put t is 0, v is 0 here, then c will be what?
0
C will be 0. Okay, so now what I can write? This will be minus vd ln 1 minus vd. Okay, e upon m. Okay, t. Now suppose there is a no that scattering force. Okay, there is no scattering force, and I am applying this electric force. Okay, and so how much time it will take to reach vd, because our final velocity is vd. Okay, my final velocity is what? My, you know Newton's equation, v is equals to u plus at. Okay, so I know my final velocity is vd and initial velocity is 0, and I'm applying acceleration, okay, to electric field. Okay, so there will be some particular time. Okay, we are explaining if there is if there is no the scattering force, then how much time it will take to get this velocity vd. Okay, without friction. Okay, so my final velocity is vd. Okay, my u is 0. Okay, so v equals to vd, my u equals to 0. Okay, 0, and I'm applying field e by m, acceleration, force by acceleration is what? E by m, force by mass. Okay, and I'm telling This time is tau. This tau is relaxation time. Okay, tau is what? Relaxation time. So I'm telling, so this in tau time. Okay, well, finally my velocity is what? My electron is colliding, and then its velocity becomes 0, and then it can accelerate. Okay, and it is free for mean free for time. That means it is free for tau period, and then it is acquired velocity, and its equal velocity becomes Vd. Okay, so between two collisions, okay, I'm repeating again, between two collisions, electrons are free. So when it collides with lattice, velocity becomes 0, and then again with field it gains energy, and it's acquired some final energy, final energy. Okay, and between this scattering, whatever final velocity it gets, okay, if you take average out, that will come this Vd. Okay, so I am here assuming there is no scattering. So how much time should take? Reality it is different. Okay, reality average velocity is Vd. Okay, but to get this, to reach this velocity, it takes some time. Okay, so in general, if I assume there is no scattering force, so this tau time it will reach the velocity Vd, and this is called your relaxation. The tau is called your relaxation time. Okay, now what I can do, I can put this value, I can replace this value by this value. So I find out tau. So tau will be what? So tau will be now Vd m EE. Okay, so put this value in this equation. Okay, so I'll get Vd equals to E upon m. Okay, so E upon m is what? Vd upon, okay, if I take from here, E upon m, so that will come Vd upon tau. Okay, so that will come my Vd upon this equation 2. Okay, so Vd minus Vd ln 1 minus V upon Vd, that will come out as Vd, okay, upon tau t. Okay, and Vd will cancel, so my equation will come out 1 minus Vd equals to minus t upon tau. Okay, and this equation is very important. This equation what we calculated. Okay, tau. Okay, so Vd, so if this equation implies Vd equals to E tau upon m. Okay, this is a very important equation. So now I got, say, this is equation 3rd. Now I'm trying to explain Ohm's law. Okay, so now I got this relation. Okay, can you simplify this relation and get Vd? If I solve this one, what will be the expression for Vd? So if you calculate Vd, okay, so Vd कितना आएगा? So 1 minus V upon Vd will be exponential minus t upon tau. Okay, and if I want V upon Vd, that will be 1 minus exponential t upon tau. Okay, and if I want the expression for V, okay, that will come out Vd 1 minus e power t upon tau. Okay, so this is the velocity velocity expression in the presence of field. Okay, when there is a field present, a reality in real crystal. Okay, when I'm applying electric field, okay, my
So here the one will come later now, because that said it was positive.
which was positive? This is
Sir,
negative, na?
Sir, after you have given it exponential,
Exponential negative.
then this one is in positive, na, sir?
Okay, exponential negative. So 1 minus Vd is this one, na? So
Right.
so V by Vd will be what? 1 minus this one. Here also 1 minus was there, na? This was this minus. Okay, are you getting it or not? भाई इसको इधर भेज दिया, इसको इधर लिया है. Okay. Now, if you see this equation, okay, so what this equation tells you?
So velocity एक time के बाद पे constant हो जाएगी.
Velocity, very good. Velocity become constant. Okay. After one thing, if t is equal to 0, okay, then your v will be, this become 0, this become 1, 1, 1, 0. Initially your velocity is 0. Okay, and when you plot its variation with time, okay, if you plot v by vd, this become constant. Okay, and this vd become 1. Okay, so these times are what? Tau, 2 tau, 3 tau. Okay, and tau is what? Elevation time. So at least 3, 4, 5 tau times. Okay, this your velocity become constant. That is the concept which I'm trying to explain. Okay, so as soon as you apply electric field on a metal, okay, that velocity of electron, okay, become constant. Okay, tau is what? Tau is relaxation time, that is equal to 10 to power minus 14 second. Okay, so compared to our experience, this time is very small. So as soon as you apply battery, okay, you get constant current because your electrons are moving with a constant drift velocity. Okay, so that's the concept I was trying to explain. Okay, now so even though applying electric field,
Voice is not clear.
yeah, so I'm telling, even though if you're applying electric field, my current is not getting accelerated, current is not getting increased because velocity is constant. Okay, now let me explain the Ohm's law. Okay, so how can we explain the Ohm's law? Okay, so we know, just now we have told the Vd is what? What is the value of Vd? Just now I calculated. And
E by tau m.
E tau by m. Okay, this is
E by tau m.
Capital E, sir. E tau by m.
Sir, in numerator, capital E will
E-
also come.
key is there.
One
Yes,
more
sir,
is
a
Yes,
capital
sir.
E.
Capital E also there, sir.
Capital E also there. Okay. Okay, E tau or capital E. Okay, so this is my drift velocity. Okay, now I know, suppose I have a conductor. Okay, and this conductor, okay, say this distance is del x. Okay, assume the charge density is n. So n is what? My charge density. Okay, concentration. Okay, number of electron per unit volume. So this is my charge density per centimeter cube, say, or per meter cube, whatever you want to say. Okay, now this is my conductor. I'm applying voltage V. Okay, cross section of this the conductor is A. Okay, so how much charge will be there in this volume? Can anyone tell how much charge will be there in this volume, in the small volume? Okay, the Q, the charge present in a small volume.
Na delta.
Okay, the charge will be what? Q. I'm writing by Q or dq. So you will be having, because n a delta x, correct, is a number, and charge also there, electron. So I can write, okay, Na delta x into multiplied by charge of electron. Okay, now if I want current, okay, if for electron you can put minus also if you want. Okay, and now if you want current will be what? Dq upon dt. Okay, so minus n a e delta x upon delta t or dt, whatever you want to write. Okay, if t is really small. So, and delta x upon delta t, what is the value? Velocity. कौन सी velocity? कौन सी velocity?
Drift.
Very
Drift
good.
velocity.
This is with drift velocity. So this is your current. Okay, now I want your current density I by A. Okay, I by will be what? Minus N E VD. J will be what? Minus N E VD. Okay. So say this is equation your 4 or 5, whatever we written last time. And now we have the expression for your this one also, VD also. Okay. So VD is what? N E. Okay. And VD is what? E tau upon M. Okay. So there only I have written magnitude. Okay. If I write in vector form, okay, this will be what? E tau upon M E, because your velocity of electron is always opposite to the electric field. Okay. So if I write minus here, this J become what? N E square tau upon M E. Okay. So this is your equation. Now what your equation says? J equals to sigma E. Ohm's law is J equal to sigma E. That means current density should be proportional to electric field. And here also we are getting same relation. Okay. It's the same relation. So say this is relation A. Say this is B. If you compare with J, you're getting electric field proportional, and these are all constants. For given material, N is constant, E is constant, M is constant. This reaction time is also constant at given temperature. So what will I become now? This is what this is. So this will compare this one. This gives me N square tau upon M. Okay, sigma. And if we say rho, okay, so rho is equal to what?
1 by sigma.
1 by sigma M upon N square tau. So this is my expression for resistivity, and I am getting J equal to sigma E type of relation, and J equal to sigma E nothing. That's Ohm's law. Okay, how can we write J equal to sigma as a Ohm's law? Okay, I have a J equals to sigma E. Okay, I know electric field E. If I'm applying voltage V, and the length of this conductor is L. Okay, so I can write E equals to what? V by L. And I can write J equals to what? I by A. So if I put here J equals to I by A, and here, and sigma is equals to, I know, 1 by rho. So if I put 1 by rho here, E is what? B by L. Okay, and I know what is my rho. I know my resistance of sample is what? Resistance sample is what? Rho L by A. Okay. And if you put the value of rho in here, so you get I by A equals to 1 by A. So A by rho will be what? RA by L. Okay. So you'll get RA by L. Okay. And you have V by L also. So LL cancel, A cancel. So you get V equals to IR. Okay. And this is a well-known expression. Okay. Obvious expression, what you know, Ohm's law. So that means classical theory, okay, we know that metals are obeying Ohm's law, and classical theory is in well agreement with the experiment. Okay, it also able to prove that V is equal to IR, because it says that J only depends on electric field. J equal to sigma E constant, and this relation. So it is able to explain the Ohm's law. Okay, that's the first point what I told we will discuss. Okay, now let me discuss the second point. The second point is that the variation of resistivity with temperature. Okay, so resistivity versus temperature graph, we have to, what we have seen experimentally, now we have to prove that one. Your with this classical, we have to see whether this classical theory is able to explain rho versus T or not. Okay, so rho versus T. Okay, conductivity as a function of temperature. Are you getting what I'm doing here? Okay, now we have to explain the resistivity. Okay, and I told you that my mvt square is nothing, it is equal to 3/2 kt. Okay, 3/2 kt. So if I want my thermal velocity vt, that will come out what, 3 kt by m. Okay, and if I know the relaxation time t is equal to mean free path upon thermal velocity. Okay, this velocity, that is both same. Okay, if you take relaxation time this way, or you take relaxation time as a what we define as a in the terms of drift velocity. Okay, so this will be this way. Okay, now if you put value here, so I'll get what, lambda upon under root 3 kt upon m. Okay, and if I write my expression of resistivity, okay, conductivity is what, Ne square tau upon m. Okay, so my rho will be what, m upon Ne square tau. Okay, so rho will be what, m, okay, n e square, and if I put the value of tau here, that is 3 kt upon m. ठीक है क्या? Okay, so let me tell me what is
लैम्डा नीचे आएगा और 3 kT ऊपर जाएगा ना, टो का वैल्यू डाल रहे हैं ना।
हाँ सॉरी टॉ को लैम्डा नीचे आएगा और 3 kt अपॉन m नीचे आएगा. Okay, very good. Okay, now if you solve this one, what this is giving to you, are you sure you are writing like this way? No, this is equal to this one. ठीक है, and this become tau vt is 3 kt upon m. Okay, m. So now for this expressions give me okay, correct. Okay, so now this expression give me what, m say cancel root m, this become 3 kt root m. Okay, and I have a ne square lambda. Okay, and from this, these all are constant. This implies what, my rho is proportional to what, t power half. Okay,
So please explain this last third step.
So here these are constant na,
Above that.
this one,
Yes, sir.
so mm cancel na, m root half, this is under root m, so under root m, so under root 3 kt m, and then you have ne square lambda. Okay, and if you write conductivity sigma, that will be simply ne square lambda upon 3 kt m. Okay, this implies what, sigma is proportional to 1 upon t under root t. Okay, so resistivity increases with temperature, this law also says. Okay, but in reality, what is the relation? In reality, we have rho is equals to t. Okay, so it is not agreement with the classical theory. The classical theory says the resistivity should be proportional to t power half, and in reality we are getting this one, rho is proportional to t. Okay, so at high temperature also this theory is not able to explain temperature variation of resistivity, and even it is even not able to explain low temperature behavior. Okay, not at all. तो लो टेम्परेचर के बारे में तो ये कुछ बोलता ही नहीं है. It does not talk anything about low temperature, and in room temperature about device temperature it says the resistivity is proportional to t power half, but in reality it's not in agreement with experimental observation. So here this theory fails. Okay, although this theory gives very nice concepts about the conductivity, okay, which is very useful fundamental concepts. This theory says your conductivity depends on what, and carrier concentration. Okay, your conductivity depends on what, and carrier concentration. So that is very important point. Similarly, if I define mobility, if I define the mobility, okay, mobility is nothing. Mobility is what, mu. Okay, what is the definition of mobility? Velocity per unit electric field, Vd per unit velocity per unit electric field is called mobility. So I know what my VD. VD is any tau upon m. Okay, and I want mobility. So mobility will be what? VD upon E, and that will be what? Any tau upon m. And if I write the value here, any tau upon m value here, n not n, only e tau upon m. VD is e tau upon m. Okay, and if I write the conductivity here in this expression, that will give me n e mu. Okay, so that means this fundamental theory, this classical theory says two important things. One thing, your conductivity depends on your carrier concentration. Okay, that's why metals have good conductivity, na? Because they have free. This n is very high in that. Okay, compared to semiconductor and insulator, this n is very high. That's why metals are good conductor. Okay, and this tells conductivity also depends on mobility. Okay, which is very important for a parameter when we will discuss semiconductor. That time we will see this is very important parameter. So even though this theory not able to correctly explain the temperature variation, but still it is very good theory. Okay, at least it's able to explain the Ohm's law, and then saying the fundamental concepts of conductivity. What is conductivity actually? Okay, conductivity depends on what? Carrier concentration and mobility. Okay, so are you getting what I'm saying?
Yes, sir.
Okay, so now this is the drawback. This is first drawback. The temperature variation is not, it's not predicting temperature variation, okay, accurately. Now let me calculate specific heat. Okay, now second drawback. Okay, what are drawbacks of theory?
This above expression will also come under this, na?
Yeah, temperature, yes, that will become temperature variation of conductivity also a drawback. Okay, the number second is if you calculate the specific heat of electron gas. Okay, what is the specific heat of electron gas? If I, so now actually the point which I want to emphasize here, that earlier we see that this theory is failed to explain temperature variation of conductivity. Okay, and it was very obvious, no, because that time we are trying to explain electron by a classical theory. Okay, and we are assuming that they follow equipartition of this equipartition theorem, actual voltage statics, while actually your electrons are fermions. Okay, so we have to apply Fermi-Dirac statics. Okay, so later when we see Sommerfeld theory will apply to explain these phenomena, then we'll see that their time we will instead of classical, we consider them, we'll take the Fermi-Dirac statics in the context. Okay, and then they will give very fine results. Okay, so this is a specific heat of electron gas. Okay, so if I want the total energy of 1 mole of gas, total energy of 1 mole electron gas. Okay, that means there are one mole electrons. So we know energy would be what? What will the energy? Total energy 3/2 Na kBT, isn't it? The energy of one electron is what? 3/2 kBT. Okay, so if there are 1 mole electrons, Na number of electrons, total energy will be what? 3 Na kBT. And if I want to calculate the specific heat of electron, that will come out what? Del U upon del T, and that will be what? 3/2 Na kb, and that will be equal to what? Your Na kb is R, 3/2 R.
3/2 R.
Okay, so it says that your electronic specific heat is equal to 3/2 R. Okay, so Are you think that this expression is correct? Because we have seen the specific
TR
heat,
आना चाहिए.
specific heat solid कितनी होती है? Specific solid
TR.
वो होती है, that is because of phonons. That is because of phonons. Okay, phonon itself is giving 3R, and experimental measure also 3R. So where is the question of electronic specific heat? When I measure the specific heat of a solid, okay, that comes out as a 3R experimentally. And when I see the contribution of phonon, that phonon itself they are giving 3R value. So this, if I assume the electron specific heat is this much, then it is a big contribution in the specific heat of phonon. But phonon itself is giving 3R. That means my actual specific heat should be very less comparison to 3R. So that should be negligible, and this is not negligible. My phonon itself giving 3R, and my solid also 3R. That means that the contribution of specific electron should be negligible. Okay, are you getting my point or not? Are you getting what I'm saying?
स्पेसिफिक 3R होती है, आप ये कह रहे हो कि इलेक्ट्रॉनिक्स इतनी ज्यादा आ रही है, इतनी ज्यादा नहीं आनी चाहिए.
भाई मैं बोल रहा हूँ कि स्पेसिफिक हीट तो 3R होती है हमारी, और 3R मेरे फोनोन जो लेटेस्ट है वही दे देता है. ओके, तो ये कहा ये 3/2R दे रहा है, तो 4.5R होना चाहिए ना. हमारा 3R में इसमें इसको ऐड कर दो 3R में, तो 4R 4.5R आना चाहिए, पर हमारा एक्चुअल तो 3R ही आता है. ओके, दैट्स मीन दिस इज नॉट करेक्ट. This is the overestimated specific value. Okay, my electron, the actual value of specific heat are 100 times less than these values. Okay, so actual experimental values actually. So first of all, specific heat contribution is almost negligible at high temperature. It gives only contribution at low temperature. Okay, but even though compared to the latest vibration specific heat, this should be very small. So this is overestimated value. Classically, why we are getting overestimated values? Because here we are considering all the electron contributing to specific heat. Okay, but while your electrons are fermions, and all the and the fermions which are near to the Fermi energy, they only contribute to the specific heat. That we'll see when we'll see the quantum theory. Only fraction of electron which is near to the Fermi level, those electrons only contribute to a specific heat. But here we are taking all the electrons. Okay, classically. Okay, so that is not true. So this is, so you're right here, actual values of specific heat, actual values of specific heat are 100 times lesser than this value. Okay, so first of all, classically what we calculated specific heat, that is wrong, and that will create further problem earlier when we see the Widman-French law. Because of this expression, we'll get the Widman-French law in error in Widman-French law. Okay, that because we are calculating here wrongly specific heat, and later when we see quantum field theory, then we'll see there how to rectify this problem and calculate exact values of specific heat. Okay, so just give me 5-minute break now. Okay, we'll start again. I hope all are you back. So let me discuss a few more drawbacks, okay, related to this same concept. So because later we have to correct those things. Okay, so it's giving wrong specific heat. Okay, now if I calculate the computation of, the third is computation of mean free path. Computation of mean free path. Okay, now if we compute the mean free path, okay, I know the resistivity formula is what? Ne square tau upon m. Okay. Now, if I can calculate tau from here, okay, then I can calculate the mean free path. Okay, mean free path is what? Vt tau. Okay, and Vt we already know. Vt is thermal velocity. We can get from 3 kT. Okay, Vt upon m. Okay, if we all know these expressions, okay, so if I know the resistivity of metal, okay, experimentally, then I can know what is tau. Once I know tau, I can calculate what is my mean free path if I know the Vt. Okay, so if I let me calculate these values. Okay, so for copper, if I take example copper at 20 degree centigrade, okay, which is nothing, 293 Kelvin. Okay, for copper at 20 degree centigrade, so the resistivity value rho experimentally measured is 1.69 to 10 raised to power minus 8 ohm. Yes.
So you've written copper at 20 degree.
Yes, 20. Yes, copper at 20 degree centigrade. For copper at 20 degree centigrade, the resistivity value is this one, ohm into meter. Okay, resistivity value is this one. Okay, and what I need, carrier concentration N. So carrier concentration for copper is 8.5 into 10 raised to power 28 meter cube. Okay, and from putting this value, if I calculate my tau, okay, tau will be what? Tau का formula क्या हो जाएगा? Rho m upon ne square. Okay, हाँ, so value क्या दे रखी है rho की? Rho की value दे रखी है 1.69 into 10 raised to power minus 8. M is the mass of electron, that is 9.1 into 10 raised to power minus 31 kg. N value is 8.5 into 10 raised to power 28 per meter cube, and electron charge is 1.6 into 10 raised to power minus 19 square. Okay, and if you compute those thing values, okay, so I should get, what is the formula of resistivity? M upon n square tau, na? M upon n square tau. I'm writing a reverse. That is, I was calculating conductivity. Okay, so tau will be what? Tau will be, okay, m upon n square tau. Okay, and if you put these values in this expression, you'll get tau value as 2.47 into 10 raised to power minus 14 second. Okay, earlier I also told the relaxation time is the order of 10 raised to power minus 14 second. Okay, and if you calculate the velocity Vt at the same temperature, Vt at
Sir, in this expression, rho will also come in denominator, na? Tau equals to m by ne square.
ne square rho. Ne square rho. Okay. Now please calculate the Vt. Okay, Vt at this temperature. If I calculate the Vt at this temperature, okay, that is 3 kT. 3 kb is 1.38, 10 raised to power minus 23. Okay, temperature is what? Kelvin, 293, and mass is what? 9.1 to 10 raised to power minus 31 kg. So exactly, if you calculate, this turns out to be as 1.154 into 10 raised to power 5 meter per second. Okay, now I know Vt, I know tau, so I should be able to calculate my lambda. Okay, and if I put these values here, okay, So my lambda, okay, comes out 2.47 into 10 raised to power minus 14, okay, into 1.154 into 10 raised to power 5, okay. And if you solve this one, how much should come? Okay, if we solve this one, it will come out as a 2.85 nanometer. Okay, so it says the mean free path is 2.85 nanometer. That means order of 1 or 2 nanometer, and that is also not correct. Okay, if this much is a mean free path, then the resistivity will be very high. Okay, this mean path, this is not actually mean free path. Okay, so actual experimentally observed value for lambda, okay, experimentally observed value for lambda is about 10 times, okay, 10 times more than this value, 10 times more than this value. Okay, so 10 times means it is order of 25 to 30 nanometer, but classically we are getting only 2.85 nanometer. Okay, this point also you need to keep in your memory, okay, because it's important point. Okay, so this is computational mean free path, specific heat. Okay, so these are the some drawbacks of this classical theory. Okay, so this portion of the resistivity portion is finished. Okay, let us do some problem from exam. Now you need to calculate this formula. Okay, this question. तो अभी तक जितना किया है मुझे सब आप लोग को क्लियर हो गया होगा. इफ एनी डाउट यू कैन आस्क मी.
सर अब तक हमने जितना भी किया वो हमने रूट लॉ को
हाँ
वेरीफाई करने के लिए किया ना.
हाँ, हम ड्यूटे थ्योरी किया. हमने ड्यूटे थ्योरी से वी हैव कैलकुलेटेड, वी हैव गिवन सम assumption of ड्यूटे थ्योरी, and with those assumption we are still doing. Okay, we have used classical theory and we have explained resistivity, and then we will explain Whitman-Franz law, Hall effect, and some optical property also. We will explain same on classical theory, taking free electron theory. Okay, and then we will do correction using Sommerfeld theory, which is more important for your exam. Okay, this is also important. The question they're asking from Dode 3 also. So they're saying the electric conductivity of copper is approximately 95% of the electric conductivity of silver. Okay, the electric conductivity okay of copper is 90% of the electric conductivity of silver. So copper की जो electric conductivity देखिए, that is 95% of silver that they given. Okay, and the electron density, okay, and while the electron density silver is approximately 70% of the electron density of copper. Okay, and the electron density of your silver electron density is 70% of copper. Okay, so using Dode model, find the ratio tau q versus tau ag. Okay, find out the collision time versus copper versus collision time silver using Dode theory. This question came in your June 2017, not very old. Calculate. What formula shall I use?
Sigma
First,
is equal to N square tau by M.
N square tau
Tau
by
by
M. Okay. So
So we cannot use this tau equals to m n e square rho. That will be wrong.
so that here they give electric conductivity, na? Then you have to take reciprocal resistivity. If they get resistivity, you can take opposite formula. Otherwise,
Conductivity is given. Okay.
okay. So if I want conductivity of copper, then this is tau will be this one, and also N is also for copper. Okay, and for also copper, and E is electron charge, and M is the mass of electron. Okay. Similarly, if I want to write the sigma for Ag, then what will come? N for Ag, E square same, tau for Ag, okay, upon M. So this is asking ratio for what? Ratio for tau copper. Okay, tau copper to 2 tau Ag. Tau copper to 2 Ag. Okay. So if I take sigma Ag upon sigma copper, so sigma Ag will be what? I want tau copper first, no? Tau copper. So sigma copper, sigma Ag will be N square N copper E square tau copper upon M divided by N Ag E square tau Ag upon M. Cancel, E square cancel. Okay, so that will give me tau copper versus tau Ag will be what? Sigma copper upon sigma Ag into, okay, this will go there. So N Ag versus N copper. Okay. Now the electric conductivity of copper is 95% of silver. This ratio should be 0.95. Okay, and a silver electron density is 70% of copper. This ratio should be 0.7. Right or wrong? Or I'm doing something wrong.
It's right.
Correct, sir.
So what should be the answer?
0.665.
0.66.
0.665. Okay, and they have given this option. Okay, so the option is what they are given 0.6 object. This is objective question, and the option D is 0.66. Okay, option D is 0.66. Okay, so this is the correct answer. Okay, let me give one more problem. Okay, the question is the number density of electron in copper is Okay, the number density N in copper is 8.5 into 10 raised to power 28 meter cube. Okay, they're asking calculate the mean drift velocity of electron through a wire of copper. Okay, when the current is, they given current I equals to 1.4 ampere passing through it. Okay, and cross sectional area of copper A is given 7.85 into 10 raised to power minus 7 meter square. Okay, and I have to calculate the drift velocity. Okay, so which formula should I use?
I is equal to NAEVD.
Very good. Okay, because we know that J is what? NAVD. Okay, and because they are not given J, they given I by A. Okay, NAVD. Okay, so I need to calculate VD. That will be upon I upon AI NE. Okay, and I is 1.4 ampere. Okay, area, for area they have already given area. Okay, A into NE 7.85 into 10 raised to power minus 7 meter square. Okay, and then they have given also your charge density 8.5 into 10 raised to power 28. Okay, electron charge 1.6 into 10 raised to power minus 19. Okay, tell me what is the value of drift velocity?
One 1.3 in 10 power minus 4.
Yes, so if you solve this one, okay, this will come out what I'm getting answer. You can check 1.31 into 10 raised to power minus 4 meter per second. Please check it. Now, the next topic is we have to discuss Hall effect. Okay, and Hall effect पे काफी questions भी आए हैं exam में. Hall effect we'll discuss tomorrow. We have to discuss Hall effect and we have to discuss that Widman-French law. Okay, we have already calculated the expression for conductivity. Okay, now we have to calculate the expression for thermal conductivity using classical theory. Okay, and we'll find out the Widman-French law using these two expressions, and tomorrow we'll see Hall effect and their questions tomorrow. Okay. So I think we should stop here today. If you have questions, you can ask me today's class. Any question?
So in the lecture, a bit I got confused
Ah.
that in the starting you stated that the free electron theory is divided into two, that is classical and quantum.
Yes.
After that, you discussed the properties of metal,
Ah.
and that
Using-
properties of metal.
Using classical theory,
Okay.
Drude theory.
Okay.
Okay, and Drude theory is called free electron theory, classical free electron theory. Okay, and this has some assumption. Okay, that electron is not interacting with each other. We have not counted electron interaction at all so far, and you can in order to calculate any properties. Then the second assumption was that electron interact with ions, that we have considered when I have written the equation of motion. Okay, when I am applying electric field, because of presence of ion scattering, okay, my the expression gets modifies. Okay, so that in part we have calculated. Third part I told that it's obey classical theory. Okay, electrons behave like gas, so that's why I use that concept, that expression for 3/2 kT half mv square. Okay, and for through those I have calculated this specific heat and this mean pre path. Okay, And but those unfortunately those values doesn't match with the experimental result, because the electrons are not classical particle. Okay, they are fermions, but still we are able to get the I told you metals obey Ohm's law, and Ohm's law means what? J equal to sigma E. Your current density depends on electric field, conductivity is constant. So those same thing we got from this theory also. Okay, and this theory is able to tell us that fundamental relations of conductivity. The conductivity depends on carrier concentration. Okay, that's why we differentiate metal, semiconductor, insulator, because metals have high electrons. Okay, and then it relates also with mobility also. Okay, that we'll come discuss when we'll discuss semiconductor. So it gives at least it at least flashes lights on some important concepts. Okay, not accurately gives the values, but gives some fundamental relations. Okay, what we need. Okay, and the more accurate will be when we will discuss this quantum theory. Okay, that will see is able to explain that variation of resistivity with temperature also, and other properties also which we are not able to calculate from field theory. Those will calculate using your quantum field theory, and remaining what will be remaining, that will be use band theory of electrons. Okay, any other question? So I'm stopping here. Okay,
Thank you, sir.
thank you very much.
Thank you, sir.